Hi, I'm Bob Hanlon, here to talk to you today about the final steps on the road to entropy. Today, talking about the kinetic theory of gases and the role of heat capacity in this theory. The issue that I want to specifically focus on today is atoms, spheres, and the difference between them. Let me get to it. As we review the key milestones on the road to entropy, these final stages, the kinetic theory of gases evolved largely from the combined work of three scientists. This was in the second half of the 19th century. So who do we have? We have Rudolf Clausius in Zurich, Switzerland. He had moved from Berlin to Switzerland. Then we have James Clerk Maxwell working out of London. And finally, Ludwig Boltzmann out of Graz, Austria. These are the three players in the kinetic theory of gases, and I want to talk some about their work. As we look at the kinetic theory of gases, what was this all about? Well, the theorists assumed that the gas atoms behaved as spheres that collide with each other while moving through space. They assumed that the molecules were comprised of two or more atoms, largely because that was all they knew. You had oxygen, nitrogen, water, hydrogen. These were some of the molecules that they understood at the time, and they also realized that there was more than one atom in those molecules. So based on these assumptions and very extensive mathematics that I'm not going to go into today, this theory correctly predicts, among other properties, the ideal gas law, PV equals nRT, also gas viscosity. James Clerk Maxwell did some great work with that, and also heat capacity. And it's heat capacity that I want to talk with you about today. First of all, what is heat capacity? A quick review. Some of you may have remembered this very famous equation, Q equals mc delta T. What do these symbols mean? Q is the thermal energy, which we call heat, which a substance absorbs. M is mass, delta T is the change in temperature, and then the C becomes the heat capacity. If we rearrange it, the heat capacity is the thermal energy added to a system divided by the mass and the temperature change. As you can see from the equation here, heat capacity quantifies the change in temperature for a given amount of heat and a given amount of mass. The smaller the change in this number here, the delta T, the higher the heat capacity. Let's look at that a little bit more. Why is this? Rudolf Clausius really started the whole question here when he really pursued the question, where does the heat go? Consider a system of colliding gas molecules here. And there's a boundary on that system, and the boundary consists of vibrating atoms at the boundary wall, and consider a heat source on the other side of that boundary. Heat flows across through the boundary and into the gas atoms. What this really comes down to is collisions at the interface between the gas and the boundary wall. It's all about colliding atoms when all is said and done. So what happens when spheres collide? Well, when the boundary wall atoms collide with the gas, you have a range of things that could happen. If the gas consists of a single atom, then the resulting motion could be motion across space, which we call translational motion, but it could also be spin motion of the atom. If the boundary wall atoms collide with a molecule consisting of two atoms with a rigid rod, you could also get rotation about that molecule. If the boundary wall atoms collide with a molecule consisting of two atoms connected by a spring, you could get vibration going on here. All of these motions are possible as that boundary wall communicates with the gas atoms. So while all of these different motions can go on when thermal energy is absorbed by a gas, it's really this motion, which we call translational motion, which results in an increase in temperature. This is where the increase in temperature goes while all of these other motions are happening. So the greater the number of different motions that exist, the higher the heat capacity, and thus the higher the amount of energy needed to be put into the system to increase temperature by a fixed amount. All of these molecules have translational energy components. All of them fly across a room. But if they're also moving and vibrating, that's energy that's taken up that doesn't go to their motion across the room. Again, there are many details here. I don't want to get into them all now, but there's a reason for talking about this. The early modeling efforts failed to predict the heat capacity of atoms. Why was this? Well, one theory is that there was no data. The first heat capacity measurements of a monatomic element occurred in 1875, and it wasn't with the noble gases, as one would think. It was actually with mercury vapor. And it was only later that the noble gases, specifically helium, was discovered in the 1890s. So there was no data around on monatomic elements or atoms to look at heat capacity. These measurements, however, of heat capacity align with the fact that all internal energy of a gaseous monatomic element is accounted for by motion across space. But wait a minute, that's not what I said on the slide before. Let's talk about this a little bit more when I look at reason 2. I believe that the reason why the early theorists couldn't predict the heat capacity of an atom had to do with the fact that they didn't know what an atom looked like or how it was structured. What do I mean by this? When I spoke about the boundary wall colliding with the gas atoms, I spoke about two different types of motion possible. One was motion across space, translational motion. The other was spin motion. Both of these are possible for a sphere. But this motion right here, not possible for an atom. It's insignificant. That the atom had spin energy reflected the assumption that the atom was solid. This just wasn't so. The early theorists couldn't even conceive of this. As we know now, the atoms, all of the mass of the atoms is in the nucleus. It wasn't until the early 1900s that we learned this. So it wasn't until the early 1900s that the kinetic theory of gases could accurately predict this. And this, I believe, is the reason why no early theorists even predicted the heat capacity of a monatomic atom. Before ending, I have a question to leave with you. Again, looking at the kinetic theory of gases. The kinetic theory of gases correctly predicts that the heat capacities of the noble gases should all equal each other, despite the wide range in atomic weights. Why is this? I'll leave this for a future video. The success of the kinetic theory of gases strongly supported the theory that matter is comprised of atoms. This was a monumental step in the road to entropy, and it was this step that served as a bridge from the classical thermodynamics of Clausius and William Thomson here, and the eventual probabilistic thermodynamic Ludwig Boltzmann here. And it's the December video I'll go into the details of what Boltzmann did. Thank you for listening to what I had to share with you today about the kinetic theory of gases. Again, I go into much more detail on this subject in my book, Block by Block, the Historical and Theoretical Foundations of Thermodynamics. See you at the next video. Goodbye.